Okay, and so I'll want someone to like, well, I'll confirm that this is definitely going live. This is fun, it's new technology, we all learn something. Okay, 20-second delay. Hey,
yeah.
Okay, it works, it works. We are officially live, everyone.
Awesome.
Okay.
That's awesome.
Okay, we're still missing some judges, students, but.
So can you decide whose screen gets showed, or is it just going to show the whole thing like every time?
I think, like if I click speaker view, I guess like on YouTube, are you asking like what's shown on YouTube?
Is it possible to turn
to just speaker view? I guess we'll wait for that 20-second delay. Yeah.
So can you like double click on my window so that I guess when the person who's speaking, or
yeah, it's I haven't figured out how to get like,
oh, somehow I can see you full screen at some point.
Yeah,
you should be able to double click. If you double click on somebody, probably they can.
I think you can pin a video also. So if you right click and pin the video, then that person remains like the center no matter what.
Yeah, because I need to be the center
well, you
the entire time. Okay, I think we should start. So is it are we all ready?
Yeah, is this view working for you on YouTube? I don't know how to. Yeah, I think you're pinned.
Okay.
Okay.
Well, welcome.
Is there? I just wanted to check if everyone is here because I had some trouble getting in with it via the link, and I had to replace part of the link with a different thing. So I just wanted to double check if you've got all the judges in particular.
The Zoom link or the
Zoom link.
Ooh. Let's see. We've got Kaushik, we've got Dave, we've got Nathan. No, we don't have. Oh, and we have Jerry. I guess I can't see everyone. Who else are we missing judge-wise?
Jason.
Jason? And
it sounds like there wasn't a systemic problem. So maybe offline and like in the background we can, because we were going to start for 10 minutes or so. So maybe Kerr or somebody can in the background just contact Jason and
we'll do.
Get him going. But I don't think that there's a systemic problem that everybody has.
Hopefully not.
It seems like most people are here.
Yeah, and Ko, will you also send it to Rong Chao?
Okay.
Just in case.
Yep.
Okay. Ooh. Oh, is it asking, Andrew, was it asking you for a username and password?
Yeah, it was. So it was asking me for username and a password if I went in with the word meeting in the middle part of the link. But if I replace that with a J, then it was letting me just join the meeting as an external participant, and then it was fine. So that was my suggestion. So maybe just the link I sent you by email, just send that to everyone, double check and tell them if they're having problems, use that link instead.
Oh my gosh, yeah. Yeah, I just got an email from Rong Chao.
Okay, perfect.
Oh. Okay, here's.
I see Jerry stole the same background.
Yeah, I like it very much.
It's very nice sort of on-point marketing.
We all have the good same idea. Hi, Andrew. I can see you.
Hey, Jeremy. Yeah. Hey.
So I mean, of course, it's very important to have all of the judges present for
Yeah, I
before
just
we
sent
start the.
Dason and Rongchao the updated link.
But I think so. We give them. It's going to be a few minutes. We'll have. I'm going to say a few things, and then Jenny and Ke will. I'll hand it over to them.
Mhm.
But so yeah. So maybe we can sort of get started, and then if we need to pause, we can pause. So yeah, I want to welcome all of you co-Zoomers, but also the external people who may be watching on our website to the PQI 2020 poster session. This is not a virtual poster session. This is real, and you're all making it real. This is live. And so I'm the director of Pittsburgh Quantum Institute. And again, I want to thank all the participants, all the 50 participants who worked hard to share your science with our community. I also want to thank all of the judges. And some of the judges are here. There's some overlap between the judges who participated in the initial selection to the final 15 finalists who will be presenting live today. I also want to thank the staff at PQI, Jenny, Ke, and Barbara, who've worked very hard behind the scenes to make this happen. And of course, we're all kind of trying to become experts at Zoom and YouTube and so forth. And hopefully it will be smooth. But I really appreciate their efforts in trying to make this, as pleasant of an experience. Of course, we'd all like to be live, in the close confines, like you can see. Actually, there was a little bit of social distancing in that picture that you can see behind in the background, but not so much. It's really an approximation of where we would like to be. But I think that this is really an important part of PQI. What we do is sharing our science and what our research, and really the focus is really explicitly on the students. This is a part of PQI 2020 that we had planned for this time actually, but this is really one of the parts of the event that I think is especially nice at the time when you can really see all this research bubbling up from students who are learning and presenting. And so I'm really happy that you are all here and that everybody's participating. So with that, I want to turn things over to our moderators, Jenny and Ke, right? So they're going to be running the show, and Jenny's going to kind of set the ground rules of how this is going to run, because we do want to stay on time, and she'll be singing, I think, the Jeopardy clock, because I think that's
now I'm going to use my phone.
Oh, she's going to use her phone. Okay.
I'm not going to sing.
So there's certain parts that are going to be timed and scripted, and so I'll turn it over to Jenny now.
All right, so you all should have received an agenda that has the list of names and what order that you'll go in. What we'll do is, you are all really good. I looked through a lot of posters at actually keeping your presentations to 3 minutes. So that's, I think, rare, and I appreciate that. But we'll give you 3 minutes to present your poster. And so at that time, you'll share your screen and hopefully use your mouse and Zoom functions so that we can all see what you're describing. And then at the 3 minute mark, we'll give you a little blip reminder. And then at 30 seconds after that, Ke or I will speak up and ask you to wrap it up. Then we'll give 2 minutes, about 2 minutes for judges to ask questions. And Ke will introduce the judges in a second. And then after that 2 minutes of questions or so, I will give judges about 30 seconds, and I'll use the Jeopardy theme for a countdown. I'm not going to sing it. For you guys to enter your scores. And so judges, hopefully you could do that live now, because you only have 3 questions to fill out. But if not, this will be recorded and you can always come back. You guys are all really good at this already, but just remember to keep muted if someone else is presenting.
Just in the interest of full transparency. So what are the questions?
Ke, what are the questions?
Yeah, so the question will be on 3 aspects. It's on your scientific content, that's 10 points. Then on your presentation, like how clear and concise and how accessible, that's 10 points. And the third 10 point is how well you answer to questions that the judges ask.
So not too bad, not too bad. And then judges, in case you are already scoring them and you don't need 30 seconds, if you could give the, there's like a reactions button at the bottom. If you could give me like a thumbs up, you can see that in my window. Then I can mark you and right, because I can't ask you to look up since you're already staring at this. So just give a thumbs up and I'll mark you. And then if everyone's done, we can continue. Okay, I think that's it for rules. Are there any questions before we move on to introducing judges? All right.
Okay, so so we're very fortunate and happy to have, I think all of them join, if I'm reading it correctly, 7 judges joining us today, including 5 PQI faculty members and 2 previous post-award grand prize winners. So we have Professor Andrew Daly calling from across the ocean at Scotland. I think there's maybe 5 or 6 hours time difference, but it doesn't look very dark there. Okay, yeah. And we also have 2 professors from chemistry, Professor David Wodak from Pitt. There are too many like screens here. Like I'm not. I think he's somewhere there. And Professor Rongchao Jing from CMU. I think he joined on last minute also. And on the engineering side, we have Professor Kaushik Dayal from Department of Civil and Environmental Engineering at CMU, and also Professor Nathan Youngblood from Department of Electrical Engineering at Pitt. So as mentioned, we also have 2 veteran post-award winners as judges today. They are on the other side of this competition now. One is Dason Waters. Yeah, I see you, Dason. Yeah, so he's a PhD candidate from Department of Physics at CMU, and also Jerry Liang. He's a PhD candidate from Department of Chemical Engineering at Pitt. So just one last note to the poster presenters. You can see from our pool of judges, they have very diverse backgrounds. So some of you may be very familiar with your work, some of you maybe not. So it's very important for you to make sure that your presentation is accessible to a broad range of audience. And I think the judges will take that into consideration in evaluation. Okay, so good luck. The first one, I think, is Ryan. Are you ready, Ryan?
Yep, I'm good to go.
Okay, share your screen.
All right. Yes. Oh, sorry. Where is that? Oh, okay, good. All right, can you see my screen? I'm gonna get into presentation mode as well. Okay, everything's good? Okay, I'm gonna start now. Hi, everybody. My name is Ryan Muzzio, and thank you for coming to this. And today I will be discussing the work that I've done under the guidance of Dr. Jody Katoch on a ARPES, excuse me, on a ARPES analysis. And so essentially, the main point I want to drive away from here is what ARPES is and what our sample is and why it's important. So first, ARPES is angle resolved photoemission spectroscopy. In that, what we're doing is we're doing photoemission. So we are ejecting electrons from a sample. If you then measure the electron's kinetic energy and angle of ejection, you can then recreate the state that the electron was in within the sample. So you can imagine after you've collected enough electrons, you then have all of the allowed filled states of your sample. So this is wonderful and very, very useful, but generally it's not done on devices. And so what we've done is we've created a sample such that we can probe in-plane electric fields as well as out of plane. So we can drive current and we can gate. And so what gating does is we can control the carrier concentration of our top layer here, which we've decided to be graphene. And so by just applying a voltage, we can change the carrier concentration. And so we're interested in how that affects our allowed states in graphene. So many of you may know that graphene should have linear bands, meaning, yes, linear bands in every energy and momentum, it shouldn't change. But what we've noticed, and they should have a Dirac point where there is a conduction band and a valence band which touch each other at a point. And so what we're doing here is taking snapshots at different gate voltages, which again, as I've said, should be different carrier concentrations, and we're seeing how that affects our allowed states in our graphene sheet. And so here you can see that there is this bottom conduction band that I've described and a bottom valence band and top conduction band, which I've described. And you see that they're not touching exactly at the point that we expected. And so we can monitor that as a function of carrier concentration here and see that the stretching is actually increasing as a function of carrier concentration. And so this is a result of our model being wrong. And it's not just a single electron traveling around in graphene, but instead you have many body interactions. And so that's just one aspect of the many body interactions that we are interested in seeing. And the other one is how the linear bands are actually not quite linear as we expected. And so here I point to the carrier concentration on the x-axis, so how many carriers we have, and then the band velocity at two separate points. So V here demonstrates the linear band, so it shouldn't change with carrier concentration. And then VF is the one I'll highlight today, and that is at the Fermi level. And so you can see that the band velocity or the slope is increasing at the charge neutrality point, which is indicative of more many-body interactions. So to conclude, we are plugging a device into this method, and we are seeing how our spectrum changes as a function of carrier concentration in a live view. So thank you for listening.
Great, thank you so much. I'm gonna open it up to, you get good timing too. I'm gonna open this up to judges. And maybe, do we wanna stop sharing screens so that we can see judges asking questions, or do you wanna keep poster?
Either way.
The judges might need to look at the poster to ask questions.
Mm-hmm.
Okay, I will bring it back up.
Do we have any questions from judges?
So I was going to, if you want to go ahead, that's fine. I go after.
No, go ahead. I'll go next. Go ahead.
Okay, so I was going to ask, so in this particular device, I was wondering if you could sort of say something about why you chose this particular device and maybe how these sorts of properties that you've been able to probe here might affect the applications of that device or the ways it might be used in the future.
Yeah, so this is a pretty well-known device if you're in the two-dimensional solids like graphene and all this sort of stuff. And so this is a pretty famous one and simple one and a well-understood one. And so what we're interested in doing is taking this community of people like transport folk who, they drive current in devices and they see how maybe a gate voltage changes and they read off the current, okay? Then there's people who do photo emission who take samples that they can't really apply external fields to, and then they can get spectra there. Now we're combining the two where we can see, okay, while we drive current, and then we are also, this really well understood device on the transport side, how does it look on the ARPES side? And so how does the many body interactions there, how do the many body interactions then change what we're seeing in the transport measurements? And so you can imagine on a much more complicated system, which we have done in a more recent study, is taking like a superconducting system. And superconducting systems are heavily relied upon understanding many body interactions. So if we take one of those systems and we can understand every single aspect of, what is coupling to what, then we can build a bigger picture onto superconductors. But that's just one example. So this is the first study that has ever been done, which was able to extract real parameters. So we needed to start with something basic. So now we can go forward and to do much more complicated systems.
That's great. Thanks. Very nice.
I think Daisang is raising his
someone
hand
else?
virtually.
I can't see anybody, sorry.
This is Dave Waldeck. I'm not an expert in this area, but I can ask a question.
Great.
Okay. So I'm looking at your poster in the middle where you do the reconstruction of the Dirac point, and you see that it's not a point, it's sort of stretched out, I guess, right?
Yes.
And so I'm wondering, how do you know it's not stretched out as an artifact of the experiment or the device, right? Maybe you've got different voltage drops across different regions of the sample for some reason. And in your ARPAS experiment, you're looking at a big area with, you know, different fields, and so the crossing points happen at different places.
Yeah, so this is a great question. So there's a few things I would have loved to have talked about if I had more time, but the first thing is that you can see the scale bar on the under the spatially resolved ARPAS map of devices. You can see that we're working on a scale about 20 microns. Now, what I forgot to mention, or what I didn't mention, was that the spot size that we're using is 1 micron. And so we can build a spatial map of our device. So we can see where the voltage drops are and everything like that. So we could take that into account. But furthermore, and if you were to do a literature search, you could see that this is a well understood property of a sample like this, where if you increase the carrier concentration, you're going to have what are called plasmons. It's just this quasi-particle that then couple to electrons. But essentially what happens is that you form a very intricate band structure within these 2 points. So it's not just a smeared out view. If you're able to construct higher carrier concentrations than we were able to achieve with this, you would see very well-defined diamond structure in there. And so not only are we looking at a very small spatial region on our sample to kind of remove those defects, what you were talking about, but also this is a repeatable thing. So you're able to go from 5 volts, minus 5 volts, all the way to 5 volts to 3 volts to, you know, any voltage, and you can see that you can still recreate this exact feature that we're seeing. So it should not be an artifact of slowly ramping your voltage up or slowly ramping it down. Yeah, I hope that explains what I was trying to say.
All right, I think since, I mean, I know Kaushik, you wanted to ask a question as well, but we're running a little bit short on time. Is it a
That's fine, yeah.
Okay, then we'll go ahead and what's our next person?
Thank you.
Thank you, Ryan.
Thank you, Ryan. Yeah, the next presenter is Yiyang Lu.
Hi, good afternoon, everyone.
Hi.
Oh, I'm gonna share my screen.
And then really quick, I think if what we do is during the judges question round, if we stop sharing screen, that might help, unless you can see everyone that does a hand raise reaction. Okay.
Sorry, I was muted. Yes, so if you click, there's ways to see everyone's raising hands. Yeah.
Okay. And then I completely forgot to do a 30-second scoring round. We'll do that next after you present. Sorry about that.
Wait, Jenny, we want to make sure that people have a chance to record their scores before they're,
okay.
You know, I think that you want to do that.
Okay, I will have a really quick, if you could stop sharing screen. Sorry, this is a little clunky. We'll do, here's a 30-second countdown. Okay. Okay, I got a countdown. Grab one phone. Okay. All right, we'll get used to this. We'll get used to this. Okay, continue on as you were.
All right, good afternoon, everyone. My name is Yiyang Lu, and my advisor is Professor Wodak. So today my topic is spin-dependent enantiospecific electropolymerization. So in this work, we successfully prepared chiral polymer from achiral monomers, and we just use spin polarized electrons to control the helical chirality of the polymer. I think this may aid in designing enantioselective selective synthesis in the future. And according to the chiral-induced spin selectivity effect, the charge distribution in chiral molecules is also accompanied by a spin polarization. Because of that, there is a spin exchange interaction between the chiral molecule and the magnetized ferromagnetic substrate. This exchange interaction will not only help separate the enantiomers, but will also play an important role in the enantiospecific reaction. Thus, in our work, we want to study further to see if we can control the hardness of the polymer by controlling this exchange interaction. So we use a nickel gold ferromagnetic substrate as our working electrode. And during the electropolymerization, we put a magnet right underneath the working electrode to induce the spin polarization. And these are the absorbance and the CD spectra of all three polymers we made. From the left to the right are polycarboxylic acid, polycarbazole, and P dot. The red curve means it is electropolymerized with north magnet orientation, and the blue curve means it is with south magnet orientation. So from all the three cases, in certain wavelengths, we can see that all the red curves are negative and all the blue curves are positive, which means we can control the chirality by controlling the magnet orientation. And here we also propose a possible mechanism based on the Kiss effect. So when we put a magnet underneath the ferromagnetic substrate, the electrons in the substrate will be spin polarized. For example, in this case, it is spin up. And during the electropolymerization, at a very early time, it will create equal amount of left-handed and right-handed dimers. However, the electron helicity in the substrate will affect the reactivity of these different enantiomers and will make the formation of, and will favor the formation of one enantiomer over the other. And when we change the orientation of the magnet, the effect will also flip. So we can make a conclusion that we can use spin polarized electrons to make chiral polymer from a chiral monomer. And we can even control the chirality by controlling the magnet orientation. And that's all. Thank you so much.
So why don't we stop sharing the screen and then we can see judges.
Okay.
They can use the reaction for, I know it's a hand clap, so that we can see if they have a question, and then we can always go back to share screen if they want to look at the poster.
I was raising my hand. I'll just hop in since no one else is. Yeah, so on your results for the polarized data, the bottom panel there, just a technical question. Why is the data so much noisier on this side than it is in the top panels?
Oh, so this, you mean for the panel DEF is much more, right. Okay. So this ABC is an absorbance spectral, and the DEF is a circular dichroism spectral. So yeah, I think since our polymer is the chirality isn't that obvious, so for the CD spectral there are much more noise here, but for the absorbance here, I think it's.
I see. Yeah, thank you.
I had a question. Could we go back to the picture of the data that we were looking at? Yeah. So if I understand correctly, the optical density is kind of a relationship to how large the polymer chains are, or the molecular weight or something like that.
You mean the intensity of the absorbance?
Right. Yeah. It looks like one magnetization has a much greater reaction than the other. Is that how
here we want to make sure that you can see the absorbance more clearly. So we move we shift one line a little above. So if you move this blue line like a little bit lower, we can intensity can match them well, I think.
So there's no preferential reaction in the north versus south pole samples?
I think no.
Okay. And what was the offset value? Is it the same for all curves?
Which one?
Just the blue versus the red, or the offset value is the same for all curves? In A through C.
A, B, C?
Yeah.
Their intensity, I think, is the same.
Okay, thanks.
All right, we're gonna try a new structure for judges to ask questions. We'll keep the share screen on and then privately write to Ke with saying question, and then he'll make sure that everyone gets a chance to tune in or chime in. Does that work for everyone, I think? Okay, I'm gonna give the 30 seconds of judging. So we'll just do this again. And if I see 7 thumbs ups, I'll stop from the judges. During this time, let's have the next post. Oh, well, never mind. You ran out of time. So our next poster presenter, Ke.
Can I interject?
Oh yeah, sure, Dave.
You need to erase our thumbs up after each time.
Oh, okay. Does it save it after each 30 seconds?
You as the host have to clear it.
Okay, I will clear it. Or everyone else, each judge needs to clear it. I always thought it just sort of disappeared after a bit, but if it doesn't, then yeah. Okay, we'll figure that out. And then Ke, who's our next poster presenter, or does someone?
Yeah, so the next presenter, I apologize if I'm not pronouncing the name correctly, is Leva or Leva?
Yeah, that's Ieva. Hi.
Okay,
hi,
I totally get it wrong.
Wait a sec.
Okay, and then for the judging, does everything make sense to everyone? Ke, you'll get a private message, and you can sort of delegate.
Sure, and also I think Dason made a comment that if the judges click again on the sum, it will clear it. Just click again, it will remove the thumbs up.
Okay, but just keep it up for that 30 seconds so I can see that everyone's done if they finish faster. Okay, I'll turn it back over to you, Ieva.
Hi, so I'm going to be talking to you about continuous variable Born machines, which was a master's thesis project I did last year in the University of Edinburgh, and is sort of still ongoing because it's a brand new method and there's quite a lot to explore. So I guess I'm going to start with a little bit of motivation. So the task that we're given is essentially to learn a continuous probability distribution. So all we're given is a limited number of samples from this distribution, and we want to train a model to generate new samples which behave as though they come from this target distribution. And we want to do this in the framework of continuous variable quantum computers, by which I mean the quantum systems should have observables which have a continuous spectrum of eigenvalues, so say modes of light and things like that. So what I mean by model is this thing called a Born machine, which in essence is just a parametrized quantum circuit or a set of quantum operations that you perform on the state. And so once you measure this Born machine or the quantum circuit, it should generate the samples that you're interested in, assuming that you've optimized the parameters of the circuit. So that is basically what we're trying to do when we're training this model. So as with any machine learning algorithm, you need a metric or a way to compare the target model and the one that you're training. So in this case, we picked something called the maximum mean discrepancy, for which the estimator uses samples from both the target and the model. And as the value of it approaches 0, you know that the two distributions are becoming more and more similar. So importantly, the reason that we picked this is specifically because it's quite easy to train because we can derive an analytic gradient of this estimator with respect to each of the parameters that were given in this continuous variable quantum computing model framework. So we can follow this gradient down to some sort of minimum, at which point we're hoping that the Born machine is producing the kind of samples that we're interested in. So I've got a nice little graph here. The main thing you need to take away from this is that there are two components to the method. There's a quantum resource, which is mostly just used to generate these samples, so it's our complicated model. And then we have a classical resource, which is used for the optimization of the parameters. And I guess you can see at the bottom there, I'm discussing something called kernels. I'm not really going to go into it because I don't think there's enough time, but basically there's just a measure of distance between two data samples in some new space. So we've got the method. We ran a bunch of experiments on this Xanadu Strawberry Fields API, so an emulator of a continuous variable circuit. You can see what the graph would look like if you have a number of iterations versus the loss. In this particular two graphs, we're investigating how robust it is against noise. And so you can also see the learning process for the actual distributions plotted out. So a classical distribution and then a very non-classical one where the samples are taken from a non-Gaussian state, a very non-classical state. And then if you're interested in terms of further research, I could go on for hours. It's a brand new method. It's very heuristic. There's a lot to explore in terms of different cost functions, different Born machine structures, what have you, sample complexity. So feel free to ask me any questions if you like. But yeah, thank you for listening.
Okay.
I haven't seen any messages, but the judges feel free to just open the mic and directly ask questions.
Sure, I'll ask a question. What's a Born machine?
So a Born machine, I don't know if you know something called a Boltzmann machine, which is sort of the classical inspiration for it, but in essence, it's just what's called a generative model. So in machine learning, a model is some sort of mathematical structure that does something you want. So a generative one generates, say, images or data samples. So a Born machine is just a name for it. It's named after the Born rule of quantum mechanics, which is basically, you know, the measurement of a system is sampling of the distribution of this observable. So that's pretty much all it is.
Okay, thanks.
I have a question. As someone who's not a machine learning expert, can you elaborate more on, I understand the difference between like the classical, your Born machine versus Boltzmann machine. How do they interplay in the learning process? So basically, like, can you take this time to describe the learning process diagram of it?
So the way I look at quantum machine learning in general is that it's basically classical machine learning, but the model you have access to is much more complex because it's quantum, in the sense that the model I'm sampling from is very difficult to build classically, but everything else is the same as in a classical machine learning method. So the samples are classical, the optimization is classical, everything I'm doing is basically the same as any machine learning model to learn a distribution, but the actual samples are being generated by something that's exponentially complex. So I have a quantum circuit of some sort. So if you know any ML, that's pretty much as simple as I can get.
Yeah. I think Jerry has a question.
Mm-hmm.
Oh yeah, can you zoom in a little bit about your figure in the last column?
Sorry, this one.
Above a little bit. Where you show the training, I think. Figure two. Yeah. So I'm curious to know, like, can you elaborate slightly more about the noise parameter value here? Because I think I'm not sure, like, whether I understand this correctly, because I think the error bar for black line here is kind of big, but I think that's because the noise parameter input is high, right?
Yes, so I should explain the error bars. I'm going to change the standard deviation, but this is over several different runs of the algorithm. And so you've got the maximum value that it reached to that iteration and the minimum value that it reached. So for all intents and purposes, it's just how much it varies. But the most important thing is how quickly it converges and seems to stay converged. And regardless, it seems to do it for basically the same time. So it doesn't really matter, I guess.
Yeah, thank you.
Okay, I think for consideration of time, we have to move on for the judging.
Thank you. I'm going to go ahead and do our 30-second countdown now. All right. I'm assuming when I only see three thumbs up or so that everyone's still going, so 30 seconds isn't overly long. All right, Amanda, where's your bread?
All right, can everyone hear me?
Yes.
Okay, and sharing my screen, can you see my screen?
All right,
okay,
go ahead.
All right, well, today I would like to tell you a bit about my work in fragmenting molecules for computational research, where often this allows us to study larger systems than we would usually be able to, or understand interactions between fragments. But it's often unclear what the best choice of fragmentation for a given molecule is. So we look to use clustering methods often used in machine learning to find subsets within our data and describe our fragments according to this information. And so what we first had to do is describe the descriptors we wanted to look at. And so we chose 5 descriptors, and they differ on what kind of molecular information they contain and how that data is represented. And we tested these 5 descriptors in 2 fundamentally different clustering methods, which are going to be agglomerative clustering and spectral clustering. And so what we were interested in seeing first is the performance of this clustering for systems where we already know the number of clusters in advance. So we begin by looking at these non-covalently bound structures, which is a collection of water clusters. And what we're looking at here, where our y-axis is going to be a measure of success of clustering, returning the clustering we expect, 1 being the best. So we see agglomerative, despite the descriptor being used, is performing really well. When we move on to spectral clustering, whoops, sorry about that, we see that in general, most descriptors are doing really well. There is one of our descriptors, these purple triangles, that just wasn't fit right for this specific method. And using this moving forward, we now have the question of what if we have covalently bound molecules? And we need to see the performance here. So we look to these set of methylthiophene tetramers, where what we expect back is to have 4 rings returned totally intact once we fragment. And so here we see agglomerative, which was working really well before, now only works for a certain set of descriptors, but spectral clustering actually comes out on top here, being more robust. From top to bottom, we want to see how this is working if we look at the level of theory of geometry optimization, so how well our structure was described beforehand. And we see a slight improvement for spectral clustering and no clear trend here for agglomerative clustering. But in general, we see that there are descriptors and methods that show promise if we already know the number of clusters in advance. So the last thing we wanted to look to is, let's say we do not know the number of clusters. In this case, we turn to self-tuning spectral clustering to choose the number of clusters for us. So here, what we're doing is looking at those water clusters again, but giving it no indication of how many clusters we want. What we find here is that only one
10
descriptor,
seconds.
10 seconds is great. That's perfect. Here, only one descriptor works well because of the way that it works with the spectral clustering, which I can explain further. So thank you for your time. And if you have any questions, please let me know.
Yes, Andrew.
Hi, so that's interesting. I'm, of course, from a completely different area. So what I'd be really sort of curious about is with this sort of clustering, what types of properties of the molecules are you then trying to use those clusters to calculate? And how do you know what makes a good cluster and a bad cluster in this type of technique?
Yes, that is the perfect question. So that's the entirely next step. I have done some work in that, and what we're looking for is we're very interested in polarizabilities of polymer systems. And so in this case, what we can look at is how well, let's say we manually fragment into what we think is important. The best we can do is matching that manual fragmentation, or sorry, the least we could do is matching that manual fragmentation, and hopefully we would see an increase in accuracy for things like total energies, but more importantly, properties like polarizabilities. So this can, the benefit of this approach though, is that it can be used pretty generically. So if there's an application you want, we can look to fragment with it and test it for whatever application people are interested in.
Interesting, thank you.
Thanks.
Amanda, Saran charging. Your question. So in your first system, in the water system, and then you compare with the second organic molecule system, I guess I missed the difference. So when you say covalent and non-covalent, what do you exactly mean?
Oh, so in these water clusters, what we're seeing is these are held together completely by hydrogen bonds between each of our water molecules.
Right.
Whereas here, we're actually bonding together each monomer. So we're seeing if those stronger interactions between our monomers are affecting clustering here.
Oh,
so
so
that's
you're saying like a polymerization, right?
Yes, yes. So yeah,
Okay,
here no polymerization, but here
right.
we're looking at that.
Okay, I got it. Thanks.
Yeah, thank you.
Okay, I think for the time we want to move on. Thank you, Amanda.
Yeah, thanks.
Thank you. I'll pull up your judging scores, and the next person can prepare their share screen.
The next person is Pratik.
Okay. And Amanda, can you stop sharing your screen?
I think Pratik can give this presentation again.
Okay.
All right.
So, just trying to share the screen.
Okay. Go ahead whenever you're ready.
Right. Can you see the screen?
Yes.
Okay. Hello everyone. I'm Pratik Khandagale from Carnegie Mellon University. I am presenting a joint work with Carmel Muzzio and Kaushik Dayal on statistical field theory for elastomers. Liquid crystal elastomers are also known as LCEs. They are composed of stiff liquid crystal molecules connected by very flexible polymeric chains. LCEs show fast reversible shape change with temperature because of nematic to isotropic phase transition of liquid crystals. Recently, liquid metal is used as an active component to get an electrically conductive LCE liquid metal soft composites. It works as an actuator, soft roller, and shape morphing material with electrical stimuli. Further progress of LCEs depends on theoretical model which can predict mesoscale response of LCE and LCE composites. However, existing models of LCE are unable to predict mesoscale structure and response. They are also difficult to adapt for LCE composites with active components. And to probe these questions, we developed a statistical mechanics-based field theoretic model for elastomers. Statistical mechanics of single chain allows us to consider chain molecular structure, whereas field theory allows us to include polymer segment-segment interaction. Diginis and Edwards observed the analogy between polymer physics and path integral methods for quantum mechanics. And using statistical field theory, We obtain partition function and total free energy as a function of deformation gradient for n polymer network for elastomer. Next, the total free energy is evaluated using a mean field assumption. And for approximating total number of chains in an elastomer network, we use a well-known Arruda and Boyce H-chain model. For a simple case of single chain stretching in no external field, we observe that the average free energy averaged over all chain orientations matches with the classical rubber elasticity result. Then numerically obtained equilibrium segment density for elastomer in 3 dimensions is observed to be as expected for the adopted 8-chain model. Next, we plan to apply the developed elastomer model for liquid crystal elastomer. We use the Meyer-Soup mean field theory for liquid crystal interaction energy. This energy depends on the angular orientation of each liquid crystal with the nematic director. Using standard statistical mechanics, then we can use the total free energy of small LC chain fragment, which will be further used to obtain the PDEs for liquid crystal elastomer chain propagators. And solution for these PDEs will be further used to obtain the complete partition function for LCE chain. Finally, to obtain the deformed structure and mechanical response for LCE material, we first allow the LCE chains to deform as per the local deformation gradient. And then we use the proposed model to get the equilibrium structure and total free energy, and thus the mesoscale response for LCE material. Thank you.
This is David Waldeck. So, sorry, it may be my fault, but what exactly are you trying to get? Are you trying to get the distribution of conformations or the most stable delta G? I didn't understand whether you were trying to get equilibrium properties or dynamical properties.
Yes, so this is the equilibrium. So like we are mostly interested to get the total free energy W, which is a function of deformation gradient at equilibrium, thermodynamic equilibrium of the elastomer. And the reason to get that free energy is that we can use the standard continuum mechanics to get the mesoscale response. So once we have W as a function of deformation gradient F, then we can get the stress strain response, which is at a mesoscale level, mechanical response of the material.
And how does that incorporate nonlinearity in the response of these chains?
So the nonlinearity is basically the W. Basically, we are interested to get a complete partition function for the chain, and the partition function is basically the path integrals over all chain conformation in 3 dimensions. And so for that, like we have this nonlinearity here. So like we have this complex functional integrals, which we convert to the mean, like the field theory using Hubbard-Stratonovich transformation. And once we have the partition function, we can get the free energy using Boltzmann factor.
Thanks.
Okay, so I think Dason have a similar question, but I think he can follow up later, and we want to move on to the next presenter, Anthony.
Okay, and I'll.
Oh, the timer, yes.
I'll run the timer. So go ahead and stop sharing your screen, and then we can bring up Anthony's.
All right. Hello, everyone. Can you see my screen and hear me okay? All right, awesome. Okay, so my poster is on a combination of the weighted ensemble strategy and hybrid quantum mechanical molecular mechanics simulations to generate pathways and rate constants for chemical reactions, as you can see in this large center block. So generating and simulating chemical reactions has been a grand challenge for chemists because chemical reactions are defined by breaking and forming bonds. And traditional simulation methods with classical potentials aren't detailed enough to capture those events. So some type of quantum mechanical potential needs to be applied to these reacting atoms, but that makes these simulations very, very computationally expensive. So in this work, I've used hybrid quantum mechanical molecular mechanics models, which is illustrated here in figure 1, where only part of the system is treated with a QM potential. In my case, it was a dispersion corrected semi-empirical PM6 method. And the rest of the system, like the solvent in this case, which is a mixture of acetonitrile and water, is treated with classical force fields. Okay, and then so that is the QMMM part of my methods. The other part is using the weighted ensemble strategy, which is shown here. And the weighted ensemble strategy works by, instead of just running a single simulation, a single molecular dynamics trajectory, we run many in parallel at the same time. And after short amounts of time, we'll stop all of them and evaluate where they are along a user-defined progress coordinate. Ones that have made progress towards our end state will be split, okay, and replicated, and others will be merged. So in this way, we can rigorously keep track of probabilities of every segment along this way, and also not introduce any bias into the dynamics. Okay, so these are the kind of two cornerstones of my methods, and I apply this very general strategy to this chemical reaction, okay, between a cation and an anion. So these two reactants just diffuse towards each other, and I simulated 3 different variants of this reactant. And now over here on the right, I show the main results. So right here is a probability distribution of all the trajectories. I had generated thousands per reactant that I simulated. And I've traced, you can see this gold, this gold pathway here is actually this target product trajectory. And keep in mind, this is not just so when I generate these pathways, it's not just intermediates along this pathway, it's a continuous movie that you can actually play of this chemical reaction. These are just snapshots. And so this is something that hasn't been done before and is very powerful in helping chemists tease out mechanistic insights. In blue, I've also traced an alternate product pathway. This alternate product was not seen in laboratory experiments. So this is one way that this method can help tease out these mechanistic insights. I promised you that I calculated rate constants. So you can see in table 1, here are the kinetic observables. And right here are the simulated rate constants, which agree very well with the experimental rate constants. And so I want to end by discussing what types of reactions can be simulated. So this is a general strategy that can be used for individual steps of a chemical reaction, but at the time it must be modeled by a semi-empirical method, and it must have less than 50 atoms in the QM region. So thank you.
Thank you. Very interesting design of the poster.
Thanks.
This is Kaushik Dayal. I was wondering if you can tell us a little bit about how you interface between the QM and MM methods. How do you handle energy or phonons and things going across the interfaces?
Sure. So the QM-MM method usually is handled by treating only the reacting atoms with a quantum mechanical potential and the non-reacting atoms, like the solvent with a molecular mechanical potential. The interaction between these two regions are purely electrostatic because there's no bonds forming between the MM and QM regions. So electrostatic interactions between these QM and MM are modeled by kind of a rough electron density of the QM region. And there are also van der Waals interactions that contribute to this combined QM-MM energy when the potentials are evaluated.
Okay, and Andrew has a question.
Yeah, so this is very interesting. As a complete outsider in this area, you sort of say that this is a very interesting problem and indeed a grand challenge. I'm sort of curious sort of in what ways your methods do things that haven't been done before. From what you sort of said, I gather that this type of calculation, this form, hasn't been done before. How far have people got before this? What is really sort of the new step? Because I guess if it's a grand challenge, people have been thinking about it for a while.
Sure. So kind of the next step that this project does that hasn't been done before, these highlighted portions, the pathways and the rate constants here. So it's not trivial, but it's not entirely computationally intensive to, for a given chemical reaction, find the transition state, perhaps find certain other metastable intermediates along that pathway. But what is really tricky because of these large computational costs are to get these very, very atomically detailed and time-resolved movies of the reaction that can provide a lot more than just these stationary pictures of what happens in between. And one of the benefits here is rate constants as well.
Great, thank you.
Okay, I think we want to move on. Jenny?
Yeah, I'll go ahead and run the timer. All right, thank you.
Okay, Anantha, you have the floor. You can start anytime when you're ready.
Oh.
Is everyone's mic okay?
Can you guys hear me now?
Yes.
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 Okay, sorry about that. I was trying to switch to earphones and I thought it would be better, but I hope it's clear enough here.
Yeah, this works.
Sorry about that. All right. Okay, so today I'd like to talk about the stability of ligand-protected gold nanoclusters under the electrochemical reduction of CO2 to CO and hydrogen. So basically, these ligand-protected gold nanoclusters are extremely small colloidal nanoparticles that are usually stabilized by sulfur-based ligands. And one of these ligand-protected nanoclusters, known as the gold-25 nanocluster that I show you here, has been experimentally probed as an active and stable catalyst for the electrochemical reduction of CO2 to CO and hydrogen. But from computational work, basically from DFT, it has been shown that in order to be an active catalyst, the gold-25 nanocluster must actually lose either one of its stabilizing ligands or a part of the stabilizing ligand to expose active sites in the form of a sulfur atom or a gold atom, as I show you here. So then an important question is raised. How is it that from experiments, we're able to see that the gold-25 is a stable catalyst, but at the same time, in order to be activated, the gold-25 must have to lose one of its ligands? So to answer this question, we turn to something known as the thermodynamic stability model. The TSM basically describes the stability of a gold nanocluster as an energetic balance between the core cohesive energy and the shell to core binding energy. So the first thing we do in this work is basically understand the thermodynamic feasibility of exposing active sites from 4 different nanoclusters that I show you here in a similar size range. So what you see from this bar graph is that the thermodynamic feasibility of exposing active sites from the gold-25 nanocluster is actually the most. And then what you see from this graph here, which is basically a manifestation of the thermodynamic stability model, is a parity plot between the shell to core binding energy and the core cohesive energy. What you can immediately see is that upon ligand removal, or rather upon exposure of active sites, the gold-25 is still stable because all these points are clustered together and close to the parity line, which means that upon ligand removal, you still have a stable, partially protected gold-25 nanocluster. In the second step, we look at how the stability of the partially protected nanoclusters is affected when you have reaction intermediates, such as the carboxyl intermediate and the CO intermediate on these active sites. And what you can again see, similar to the previous trend in these parity plots, is that when you have the carboxyl intermediate or the CO intermediate on the active sites on the gold-25 nanocluster, these points are still close to the parity. And this is important because this means that these intermediates are actually acting, or rather playing the role of these ligands, of these stabilizing ligands, and maintaining the stability of the gold-25, thus explaining experimental observations related to the stability of the gold-25 nanocluster as a catalyst. Furthermore, we try to probe the electronic interactions of the carboxyl intermediate when it's present on the sulfur active site and the gold active site of the gold-25 nanocluster. And we hope that when we see a splitting of the simulated optical spectra peak, that we can help experimentalists detect reaction intermediates. So in summary, we were able to use DFT and thermodynamics to explain experimental observations related to the gold-25 nanocluster and provide a guide for experimentalists to detect reaction intermediates. Thank you.
Any questions? Jenny, do you have any question? You're the ligand.
I know, and I wanted to pay attention to this one, but I was getting something up with the timing. So I can.
So I'd be happy to ask if you'd like. I'm sort of this is very much outside my field. So I'm curious, in terms of the catalytic activity you're talking about, are these things ultimately that are catalysts for processes that we're interested in chemistry, or is it something that's industrially relevant? Is it something that's interesting for biochemistry? Where are the sort of applications of these things, and what impact do you see the research that you've done here having on those applications of the materials that you're studying?
Yeah, it's a great question. A very dense question actually to kind of unpack, but I think the main thing right now where we are in terms of doing research with these nanomaterials is looking at, for example, in this case, the electrochemical reduction of CO2, because CO2 conversion is something that's a global challenge. We want to try and convert CO2 in sustainable ways, and that's why we look at electrochemical methods of reducing CO2 to other valuable chemicals. So for example, here we can convert CO2 using these gold nanoclusters to CO and hydrogen, which can be syngas, and then which can again be precursors for industrially valuable chemicals such as methanol or higher hydrocarbons, right? So right now, I think we're at the stage of testing these at a lab scale. And I think that the uniqueness of these materials is that they have atomic precision. So if you see this, if you can see my cursor, the gold-25 nanocluster, the structure of the gold-25 nanocluster has been exactly determined. So you know exactly the number of gold atoms and the number of ligands that are present in the structure of these materials, and so it makes it so it's very nice, and it's a good way to use DFT and computational methods to probe the properties of such nanomaterials. So I think these can be used eventually as templates for synthesis of, say, for example, less expensive materials that can be used industrially. So there are kind of two ways of looking at this.
Thank you.
Okay, thank you very much for the comprehensive response. Maybe we give some time for the judges to evaluate, and Jingchen is next.
All right, you can bring up your screen, Jingchen. Okay. All right. If you guys want, I could get my mellophone and play the next one live, but I won't. Okay, go ahead, Jingchen.
Vote for that. I want that.
Okay. Hello, everyone. My name is Jingchen Zhang. I'm a graduate student in Professor Tom Purdy's group. Today, I want to talk about the quantum optical level sensing on a silicon nitride string. So quantum measurement necessarily includes back action, which describes how much the measurement process affects the system being measured, and is limited by the Heisenberg's uncertainty principle. Here we did a quantum measurement in an optical lever to study the properties of quantum back action. One optical lever is a cantilever where light bouncing off the surface of a tilting nanoresonator is to prove the angular deviation delta theta. The back action in our system is the torque delta t, which is because of the kicked angular momentum due to the random locations at which the photons get recoiled on the lever. In order to get to the quantum regime where the quantum back action becomes important, we need to reduce the system noise as much as possible. And that consists of the majority of this work. In order to reduce the thermal noise, we designed and fabricated the silicon nitride strings with ultra high quality factor, which means that its mechanical energy decays into the environment very slowly. We imposed ultra high stress on the strings such that the effective mechanical loss is minimized. And we did the periodic modulations of our structure to create the acoustic bands to trap the defects mode within the band gap to reduce the clamping and radiation losses. And here is the design of our structure. This is the band structure of our samples. We fabricated our device and we performed the ring down measurement to measure the quality factor of our devices. Here is an example figure of the quality factor of 10 to the 6th, which is already very high, which means that the thermal noise is very slow on our sample, but we aim at 10 to the 9th, so more efforts are yet to be made. In order to reduce the noise from the laser, we performed the balanced measurement to cancel the intensity noise of the laser and to characterize the intrinsic noise of the laser. Here is our result. We saw that the intrinsic laser noise is linear with respect to the optical power, which shows that we can almost completely cancel the intensity noise of the laser. And our intrinsic noise is quantum shot noise limited. On the other hand, we are designing an auto balancing system to better cancel the laser intensity noise. And here is the optical diagram. In the next steps,
10 seconds.
Other than reducing the thermal and laser noise, we plan to create the destructive interference between the angular deviation and the back action torque to lower the system noise to the standard quantum limit or even lower. Thank you.
Okay, Jason, finally your turn.
Yeah, actually, can you go to the ring down measurement?
Yes, sure.
So I just would like a little bit more explanation of what you get out of that. You get a Q factor out of this, but what information are you getting out of this? Like, what does the next generation look like? What do you want to improve in the signal, etc.?
Sure. So in a typical ring down measurement, firstly, we shake the sample with a piezoelectric shaker on the two sides up with a typical shaking frequency of 0.5 megahertz. And then we stop the shaker and measure the exponential decay of the mechanical energy. And here is the y-axis is the log scale, and we saw a linear relation, and we can measure, say, this the decay time, and from the decay time we can induce the quality factor combining the intrinsic resonant frequency of our sample. And to improve the quality factor, we want to work on better design of the sample. For example, we can change the shape of our sample to make this, say, sharper, or to create a sample so that the energy are more focused in the middle. That can increase the quality factor, like theoretically.
Thank you.
Yeah.
Okay, thank you. Oh yeah, go ahead, David.
Yeah, I had a really simple question. Maybe it's naive over where you have Heisenberg's uncertainty principle. I thought the natural conjugate variable of the angle was the angular momentum, not the torque.
Yes, that's correct. So
am
here,
I missing something?
Yeah, that is absolutely correct. So here the torque is the change of angular momentum per second. So here we and the torque is directly related with the experimental observable. So here we put the torque as the conjugate variable, but it's actually the angular momentum per second, and you're absolutely correct. So actually, the change of torque can be converted into relative noise in the signal, and that's a direct observable.
Okay.
Yeah.
All right. All good, Dave, and everyone else? We're going to move on with the judging round, and then Shubham, if you could get your screen shared. All right, and I'll turn it over to you. Go ahead when you're ready.
Hi, I'm ready. Can I start?
Yeah, go ahead.
Okay. Hi, I'm Shubham Avte, and I'll be talking about high-speed 2D memory based on ion gating using a monolar electrolyte. So let me introduce the ideal gating or ion gating. So ideal gating has like, if you have an electrolyte on top of a channel with oppositely charged ions, like here there is a channel and we have an electrolyte with oppositely charged ions. And if you apply a bias, charges moves towards the oppositely charged terminals. For example, here, if we apply positive gate voltage, anions will move towards the gate and the cations will move towards the channel. And these cations will dope the channel with oppositely charged image charges. So the ideal gating offers high capacitance densities, which can offer low operating voltages. But our group has developed a novel monolar electrolyte, which is this molecule here, cobalt crown ether phthalocyanine, that has 4 crown ethers, and each crown ether can solvate 1 lithium ion. And this can lay flat on top of a channel. For example, here, we have reduced the thickness of this electrolyte down to a single molecular layer on top of a channel. So we have electrolyte at the limit of scaling. In this poster, I'm going to talk about high switching operations of the device. So this image here is a cross-section schematic of the device we fabricated. We have a WSC2 as our semiconductor. We have a monolar electrolyte and an HBN on top of it. So the on state when the lithiums are close to the channel, and the off state when the lithiums are away from the channel. This image here is an optical image of the fabricated device. Let's look at the electrical properties. This image here is a programming sequence we use to demonstrate the bistability. What we do, we apply plus 30 volts to the back gate that actually pushes the lithium away from the channel and makes the device off because there is no doping now. And then we apply minus 30 volt for a second that will attract the lithium towards the channel and make the device on. So this is the output of this programming sequence. So the red curve here are the repeats of the off state programming, and the blue curve here is the repeats of on state programming. So if you look at backgate voltage of 0 volts, you can actually see 2 different current levels. This is on state and this is off state, which are different by 4 orders of magnitude. That means when we apply plus 30 volts or minus 30 volts to the backgate, we can dope WSC2 FET, either P-type or N-type, and this programming remains after the bias is removed. People say ions are slow, but if you ask them to move a short distance, they can do so in a short time. So let's look at high-speed performance. This image here is a drain current with respect to program pulse width we apply. That means we apply plus or minus 30 volts for this period of time, and then we see the drain current. So the flash memories we carry in our pockets operates in this region, that is 100 microseconds to 1 milliseconds. But with this ideal gated device, we have been able to demonstrate the on-off ratio of more than 3 orders of magnitude for the pulse width down to 50 nanosecond. We have also shown the endurance of the device for 1000 cycles with the pulse width of 50 nanosecond, and we still retain the on-off ratio more than 3 orders of magnitude. With that, I would like to conclude. We have demonstrated high-speed 2-dimensional solid-state memory based on ideal gating using a monolar electrolyte. And I would like to thank our collaborators, Dr. Benjamin Hunt from CMU and Dr. Feng Xiong at UPIT, and also the funding agencies and NSF Career Award and AAAS. Thank you.
Thank you, Shubham. A very nice haircut. Time for
That's
questions.
by myself.
Hey, great talk. This is Nathan. I just had a question regarding your programming array cycles. So you go to 1000 cycles. Have you tried anything beyond that? Do you know what's limiting the cyclability and endurance of your devices?
So there is nothing that is limiting the endurance of the device. We only did programming for the 1000 cycles because of the use of the equipment. Because we do not have the capability in our lab to apply the nanosecond pulse widths, and because 1000 cycle measurement takes like about 8 hours, and since we use like user facility, we had to limit the endurance measurement to 1000 cycles. But I'm pretty sure that we can have more than 1000 cycles endurance on these devices.
Okay, great, thanks.
Jason raised his hand.
Real quick question. I'm assuming these are operating at room temperature?
Yes.
Yeah.
Yeah. So all these measurements were done at room temperature in vacuum.
Okay, thank you.
All right, I'm going to start the timer.
Brian, you're next. Yes.
Dog. All right, great. Thanks. Go ahead, Brian.
Sorry, I'm on the wrong slide. All right, can you see and hear me? All right, great. So today I'd like to present to you my poster titled Computational Design of MOF-based Electronic Noses, Henry's Coefficients for Complex Gas Mixtures. But first I'd like to answer the question, what is an electronic nose? So an electronic nose is simply an array of different gas sensors designed to mimic a biological nose. And for context, despite advances in sensing technologies, a dog's nose actually remains the best available to us in terms of portability, sensitivity, and selectivity. So we wanted to challenge ourselves to design a portable electronic nose, which could rival a dog's nose. And so to do that, we turned to a class of materials known as MOFs. So MOFs are nanoporous crystals, meaning they're readily simulated with record-breaking gas adsorption capabilities, making them perfect for this application. And so our method so far had been to choose a set of MOFs we want to look at, simulate them with GCMC, giving us a library of absorbed masses as a function of both MOF and composition. And then, so given a set of experimental masses, we can actually compare them to our library of simulated masses, and for all compositions, assign a probability. So then doing that for each element in the array, we would get an array of probabilities, which can be combined into a joint probability for the array, improving the prediction capabilities as seen here. So although this method was really exciting, it was limiting in that for any composition we want to predict, we need to do a distinct simulation for. So as you start to look at complex gas mixtures, the computational overhead is explosive. So to get around this, we actually turn to Henry's coefficients. So Henry's coefficients simply quantify a linear relationship between the amount of gas absorbed and its concentration in the bulk. And so we decided to develop a library of Henry's coefficients for gases with a background of air, bringing up the question, how does this background gas actually impact the predicted Henry's coefficient? So to answer this, we ran simulations for 3-to-1, 4-to-1, and 5-to-1 background gases of nitrogen and oxygen with the Henry's gas. And so as you can see from the top 3 plots, the set of points from all of those simulations lie directly on top of each other, meaning that the Henry's coefficients are valid over a variety of compositions. So with these Henry's coefficients, we revisited our prediction method. And so like before, we would create a set of points in composition space and convert them to mass space, but this time rather than doing that with a distinct simulation, we could just use the Henry's coefficients, which offered us a lot of flexibility and speed that we didn't have before. And then so with our previous method, we could still assign probabilities, filter out these probabilities, return to composition space in an iterative fashion until we actually converge on our composition. And so with this method, we analyzed a set of breath samples for the detection of liver disease, for which ammonia is a biomarker. So on the top, you can see how the algorithm proceeds for a typical breath sample. And on the bottom, you can see the results between healthy and diseased samples. And so even with this slight systematic under prediction, we can still distinguish between the two really readily. So we're excited to see where else we can actually apply this electronic nose design. With that, I'd just like to say thanks and take any questions.
Thank you. And very nice way of using the Zoom function. I hope our tutorial online is any use to you.
It was exactly from the tutorial, so thanks.
Yeah.
Could you just elaborate on how the surface acoustic waves play a role in your device?
So the surface acoustic wave sensor is just what we chose to model very roughly. But the idea is just that the signal is proportional to the absorbed mass. And so really on our end, we work entirely in terms of mass data. The surface acoustic wave would come in on the experimental side, and then we would just have to map from the voltage of the surface acoustic wave device back into mass space. But once you make that transition, everything is same methodology-wise. So you could use like a quartz crystal microbalance. We're looking into like conductivity sensors. So you can really change out the sensor type as long as you can still get this library of signals.
Great, thank you.
Yep.
All right, if there's no further questions.
Yeah. Sorry, I have one quick question. So I noticed that one of your Henry's coefficients is calculated with nitrogen oxygen 4 to 1. So that is quite close to the air composition, right? So did you use that for calculating your final figure?
So I didn't have too much time to go into detail, but actually on these three plots here, there's 3 points on top of each other. They're just so closely stacked that they look like a single point. So for each of these, there's 3 to 1, 4 to 1, and 5 to 1. I obviously chose them because they're close to the composition of air, but that's to say that like if the oxygen and air gets reacted and it approaches like 5 to 1, that Henry's coefficient I predicted is still valid for this range. And like similarly, if something happens to the nitrogen and it goes towards 3 to 1, it's still valid. So I have some flexibility. I don't need a new Henry's coefficient every single time the background composition of air changes, which was really exciting because of the flexibility it provides us.
Okay, thank you.
Yep.
All right, great. Now for the judging round and the next presenter.
Thanks. Let me
We have 5 more presentations.
All right, go ahead, Dana.
Hi. Hi, I'm Dumi from Levy Lab, and today I'll talk about our efforts on surface acoustic wave generation and detection on lanthanum illuminate strong-tip timing. Nowadays, many people are seeking solutions for grand challenges in quantum mechanics, and the ability to control single electron is essential for quantum electronics. Surface acoustic wave provides great possibilities on reaching this, and it can act as the electron shuttle, allowing fine manipulation to the electrons. The system we're working on is lanthanum illuminate strong-tip titanate heterostructure, which is a kind of complex oxide. It combines the rich physics from the correlated materials to the nanoelectronics. With the tunable metal-insulator transition property, we developed the conductive AFM lithography technique at the LO-STO interface, which can be used to pattern nanostructures such as nanowires and tunneling barriers at the interface. Implementing this unique technique, we have tried different devices at the interface, and one of them is this single electron transistor. Basically, it's a nanowire with two barriers to isolate it from the source and drain, form the quantum dot in the middle. So this is a very nonlinear device, which means it can be used as the radio frequency mixer, mixing two different radio frequency signals and giving us the difference frequency signal. So we use this device as the detector for surface acoustic wave. To generate surface acoustic wave at LO-STO interface, we use this interdigitated transducer device. Basically, it's a metallic column structure. When we apply positive and negative voltage on each side, there will be electric field forming in the middle, looks like this. When we apply an AC signal to it, the electric field will flip its direction back and forth. With the piezoelectric property of the material, the surface acoustic wave can be generated in the material. So we combine these two devices together at LO-STO interface and create them with conductive AFM lithography technique. In the device, we put single electron transistor in the middle of a pair of IDT structures, and we did a control experiment compared with the experiment itself. First, we apply a AC plus DC voltage to the side gate to tune the single electron transistor, and it shows the tuning effects looks like this. After that, we turn off the AC part and turn on the surface acoustic wave generator. We can see a similar tuning effects, which is showing that surface acoustic wave is tuning the single electron transistor, acting like an AC side gate. Taking advantage of strong tip tightness piezoelectric property at cryogenic temperature, we also did the experiments at 2 Kelvin with a pair of IDT structures patented by MBTIN and use a VNA to measure its scattering parameters. From the transmission parameter, we can see a clear resonance coming from surface acoustic wave. And this resonance signal can be efficiently tuned by applying a backgate voltage to the substrate, which is related to the tuning effects of the dielectric constant of the material. And later on, we would like to keep working on single electron transport within surface acoustic wave and put nanowires in the middle of a pair of IDT structures. And that's all. Thank you.
Thank you very much. Any questions?
I have a quick question. So can you zoom in a little bit for the results part on the third column on top? Yeah.
Yes.
So I just I was amazed by the side gate effect. So it's but I just want to know, is there any further plan to, how to say, like kind of improve a little bit the output? For example, your red curve.
Sorry, you mean the data here, how to improve it?
Yeah, so is there, because I'm not sure whether, because I'm not in this field, so I'm not sure whether, for example, the noisy, a slightly noisy output in the red curve can interfere the performance of your device. I'm not very sure about that.
Of course. That's a good question. I think we can improve it by from both software part and the hardware part. We use a deck cards to like take the data that might have noise itself, and we use lock-in measurements. I think lock-in measurements itself is good, but definitely there's ways to improve it.
All right, thank you both. Is that all? All right, then we'll move on to the judging scores. Thank you so much.
Thank you.
All right, go ahead when you're ready.
Hello, my name is Hisan Lim in Herboy Petex Group. Here I want to briefly show my research on the important d orbital contribution to electronic structure and absorption behavior of calcium. So first, I want to explain why I focus on the d orbital in calcium. D orbital in calcium is energetically very close to their valence s orbital, showing the characteristic transition metal chemistry and topological band structure by a high d orbital participation, even if there is no electron in the states. So the main question in this study is that how the orbital character affects the electronic structure and absorption behavior, and what is the main difference with other S-block elements such as alkali atom system. For this study, I performed the complementary spectroscopic and microscopic method using multi-photon photoemission spectroscopy and scanning tunneling microscopy. So first, my experimental results show the 3-photon photoemission spectra during calcium evaporation. Compared with clean silver, which has only surface state spectral feature, I found the new spectral feature A and B at the different energy position induced by calcium. To assign this new spectral feature, I plotted final state energies depending on the photon energy shown in figure B. In this multi-photon photoemission process, according to the photoelectric effect, the slope and the intercept value indicate the photon process and energy level position of each state. Here in 3-photon process, 2 of peak A and slope 1 of peak B indicate the unoccupied state located at 1.7 electron volt and 2.8 electron volt. And also the long wavelengths, I also found another spectral feature which has a slope 3. It indicates the occupied state of calcium below the Fermi level. Finally, I complete the electronic structure with 3 calcium-related states having a significant D character verified by DFT calculation. Interestingly, I found the distinct spectral feature between 2 unoccupied states A and B, showing that only peak B is highly sensitive to the coverages. This contrasting behavior of spectral width and the final state energy typically suggests the electron delocalization by atomic condensation, which is also confirmed by coverage-dependent STM and absorption site-specific STS measurement. Therefore, 2 calcium-induced unoccupied states are assigned to 2 different calcium phases, even at the low coverages. At the initial stage, calcium atom preferentially observed at the step edge shows the characteristic sharp unoccupied state A here. And once our step edges are covered, calcium atoms start interacting with other atoms and form the island by metallic condensation, showing the broad peak B. This unique and totally different behavior with other S-block elements can be explained by the significant d orbital participation, which stabilized the interatomic interaction. Recently, I found graphene-like hexagonal structure of high coverage calcium and unique spectral feature, which has a negatively dispersive spectral feature at the gamma point. So I want to study this uncovered spectral property, and further I will extend my research to calcium-based electrolyte material. Okay, thank you for listening.
Thank you very much. We have questions?
This is David Waldeck. I have a question. So you are extracting the energetics of these surface localized states through the spectroscopy, right? But
yes,
can't you also do that using STS? And so I'm wondering if you do that, how do they compare with each other?
Yeah, I already.
Or did I miss that?
I attached the figure, but I didn't explain that. So this is the STS data. So I measured the different absorption site, the calcium observed the different absorption site. So when I measured the step edge, there is a very sharp peak at 1.7 electron volt, which is very agreement with this sharp peak. And when I measured the calcium island, depending on the island size or shape, the energy position is a little bit different, but I can clearly find the broad spectral feature at 2.8 electron volt. So which is also agreement with my spectroscoping result.
Oh, that's very nice. Thank you.
If there are no other questions, I'm going to go ahead and start the timing, judge scoring. Thank you very much.
Thank you.
All right.
The next one is Mu Qing. Feel free to share screen.
Hello, can you hear me?
Yep.
Yeah, and we can see it.
So today my talk is on nanoscale metal-to-insulator transition in freestanding lithium aluminate strontium titanate membrane. So we all know lithium aluminate strontium heterostructure bears many interesting properties, and in our group we are particularly interested in tuning the metal-to-insulator transition at LAO-STO interface with conductive atomic force microscope lithography. If the LAO layer is just under 4 unit cells, when we use a positively biased AFM tip to sketch on the LAO surface, the interface beneath the tip becomes conducting. Meanwhile, a negatively biased tip can restore the interface to an insulating state, which can create this barrier. So using this technique, we can create various nanoelectronics such as single electron transistor and electron waveguides, which reveals the strong electron-electron correlation of the system at low temperature. And in the meantime, we keep thinking how we can integrate LAO-STO heterostructure with other materials to develop a new generation of versatile nanoelectronics broadly integrable with different material platforms. For example, integrating with flexible materials, ferromagnet, other superconductors, and silicon-based architectures, or even silicon quantum dots. But directly growing LAO-STO on other non-perovskite materials is proven to be really hard because of the structural and chemical mismatch. So here we think of the chemical release method. So we grow LAO-STO on a thin layer of strontium ruthenate, and then we selectively etch the SRO layer away to release our LAO-STO membrane, which is then transferred onto other substrate, in this case, a silver substrate. We now can achieve millimeter-sized membrane transfer, and the surface morphology and lattice structure is well preserved during the transfer. And then after patterning gold titanium electrodes to contact the LAO-STO interface, we performed our conductive AFM lithography to try to make this 4-terminal nanowire device at the LAO-STO interface. And we noticed as soon as we finish writing this main channel, which is this yellow line in the middle, we can see a conductance jump over 2 microsiemens. And when we sketch with a negatively biased AFM, sketch with a negative voltage across the nanowire we wrote, we can see the conductance drops back to 0. And the nanowire width extracted from this writing and cutting process ranges from 15 to 20 nanometer depending on the writing voltage. And then we also cooled a nanowire device down to dilution fridge temperature and saw some non-linearity in the IV measurements. The differential resistance dip near the zero bias can be explained by some possible superconducting regions across the device, since this dip can be suppressed when you elevate temperature and magnetic field. So in conclusion, we achieved transfer and conductive AFM patterning of freestanding LAO-STO membrane, which serves as the basis to create extremely customizable nanoelectronics on a variety of material platforms. Thank you. So I'm finished. Can you hear me?
Yeah, yeah.
Oh, sorry.
Sorry, good job. Thank you. Are there any questions?
I have one.
Judges or anyone?
Not,
Jason?
Yeah. Can you zoom into the low temperature results, please?
Mm-hmm.
So I'm assuming that you're attributing the gap-like behavior to potentially superconducting because it vanishes with temperature. Can you extract a gap size, and like how does that compare to, say, a BCS model or something like that? Like it looks like maybe a critical temperature of 150 millikelvin.
So the critical current here, I think, is around 5 nanoamp, and I did not particularly extract the gap size because I forgot what the corresponding sourcing voltage is. Sorry, I did not do that, but the critical temperature which is around 200 millikelvin and the critical field which is around 0.1 Tesla corresponds, is very similar to what has been found in bulk LAOSTO.
Okay, I think Andrew has a question, and after that, we're going to move on to Sydney.
So these are obviously very interesting experiments and very interesting materials. These sorts of interfaces have been studied, obviously, in the group that you're in for a number of years. I'm wondering, in this sort of fabrication technique you're talking about here, what are the things that, or what are the new properties, if you like, that you can produce, or what is better about the way that you're doing this than how things have been done in the past?
So I think here we have the potential to put LAOSTO on literally any other materials, because earlier we can only use the bulk to pattern some devices to study the property of LAOSTO. And now, since we can combine with other materials, we can see like how the effect of strain and other proximity effect have any influences on the 2D electron guides to our LAOSTO system. And furthermore, we can use our LAOSTO nanowires to gate other silicon-based electronics, such as we can use it as gates for the quantum dots or something fancy like that.
Very nice. Okay, thank you. Sorry, I said it should be 3.
Yeah.
All right, thank you both for your questions. Thank you, McKing.
Yeah, thanks.
All right, and here's the timer. All right, thanks. And Sydney, you can go ahead when you're ready.
All right, can you hear me? Okay. All right, my name is Sydney Brooks, and I'm a student in Professor Rosie's lab. And broadly, we're concerned with rational materials design. And today I'm going to be talking to you about peptide sequence modifications for assembling gold nanoparticles into chiral plasmonic helical superstructures. So to begin, chiral assemblies of nanoparticles are of great interest due to their potential in multiple different applications, such as plasmonic metamaterials. But in order to access this promise, we need to have precise control over the structural design. This can be accomplished through the use of highly tunable assembly scaffolds, such as a peptide-based assembly method that we have developed within our group. And so within this design platform, we have a molecule that consists of organic tail attached to a peptide head group. And so you can change the identity of the aliphatic tail as well as the peptide sequence, valency, and chirality. And so using this design, we have produced a wide variety of different structures, including these single helices which consists of an aliphatic tail attached to 2 of the peptide head groups shown. We also demonstrated within the system, we were able to use the aliphatic tail in order to control the pitch of the helices as well as the particle size and dimensions. We also determined that a decrease in pitch led to an increased chiroptical response. And so obviously the next steps would be to decrease the aliphatic tail as much as possible in order to maximize that chiroptical signal. However, we found once we went down to 14 carbons, the molecule no longer assembled into fibers, and so it remained in solution and yielded only discrete nanoparticles. And so the goal of this research was to take the peptide sequence and use rational modifications in order to increase the hydrophobicity of that sequence in order to regain the assembly in the aqueous buffer. And so we designed a series of peptide conjugates to accomplish this goal. So we subbed out the 4th amino acid in that sequence, which was a serine residue, for threonine, and then phenylalanine for a hydrophobicity gradient as it increased. And so we first studied the peptide assembly within an aqueous buffer, and we found that only the phenylalanine variant assembled. So we were able to observe those fibers via TEM and confirmed via CD, FTIR, and AFM. And we also demonstrated that they form these twisted ribbons when we examined them via AFM with a pitch of around 65 nanometers. And when we studied the nanoparticle assembly, these results agreed nicely with what we had already shown. And so only the phenylalanine variant directed the assembly of these helices. And additionally, the helices from the C14 phenylalanine molecule had a pitch of around 67 nanometers, which is down from around 80 nanometers for the C16. So we were able to show that decrease in pitch. And then just as a add to this project, we also wanted to further test the modification strategy in order to see if it was viable in other assembly systems, specifically the double helices that were previously studied. These arise from the conjugate C12 pepgold. And so we postulated that the aliphatic tail would have a similar effect here. And when we synthesized the same series of conjugates, we found that the results correlated nicely. We went from unassembled with X equals when the molecules were serine and threonine to assembled with phenylalanine. And so overall, we demonstrated that we were able to affect grand structural changes with just a single amino acid mutation. Thank you.
Thanks, Sydney. Open up the floor to questions.
So I was wondering if you could maybe say a little bit more about sort of how these materials would be used, sort of in the sense of as metamaterials or so on. This is obviously, you know, things that are relatively small. This is a very different field to what I'm familiar with. And I'm curious sort of how they'd be used, how they would be probed, and, you know, ultimately maybe how they might be used.
Yeah, so because we're using metallic nanoparticles that then have plasmon resonance, when you study these, they have an optical signal around, these ones are around like 650 nanometers. And so if you excite those, then they have this really large characteristic signal that can be observed. And so specifically for different types of sensors like SIRS, that can be really helpful when you're trying to detect chiral molecules.
Okay. This is very interesting.
Thank you.
All right, thanks for your...
Oh, sorry, could I follow up with a question? So if the plasmon resonance is at 600, but the chirality seems to be at the ultraviolet, does that, can you comment on that?
Yeah, so in the middle figure, what that is measuring, so we're measuring the peptide secondary structure. And so that's just to track the beta sheet formation in order to visualize the fibers forming. So those spectra are taken without any nanoparticles.
I see. Thank you.
Yeah.
All right, thank you all. And then we're moving on to our last presentation, but we'll have our scoring round. Thanks, Sydney.
do I stop? I'll share.
Okay. All right. Looks like you're all set. Go ahead when you're ready.
You're still muted.
All right, sorry about that. So hello everyone, thanks for staying till the last one. My name is Shen Li. So today I'd like to present my prediction of second Zhang from a Monte Carlo simulation. So second Zhang is a phenomenon of wave-like heat transport. So the major heat carrier in solid is called phonon, which is a quantized atomic vibration. And in some cases, these phonon particles will behave like fluid molecules. And for molecules, the acoustic sound is the propagation of a pressure pulse. Similarly, for a fluid like phonon flow, a temperature pulse can also propagate, and that's what we call second sound. Observing second sound is scientifically important because it confirms that the heat transport in discrete lattice can result in both momentum conserving and momentum destroying scattering. And it is regarded one of the great triumphs of the theory of lattice vibrations. But previous experiment was done at extremely low temperatures around 10 Kelvin. And there is no experimental work that has directly observed the propagation of second sound at much higher temperatures. So our simulation has first principles accuracy, and we aim to predict second sound and provide important guidance for the experiments. So the material we are studying is one slice of crystalline graphite, and we are simulating 1/4 of a ring-shaped pump laser that heats up the sample. So we use a density functional theory to calculate the relaxed atomic structures and interatomic force constants. Then we do the lattice dynamics calculation to calculate the phonon properties. These calculations are done at nanoscale. And phonon exists in a mesoscale, and the transport of phonon is governed by the Peierls-Boltzmann equation. So we use a Monte Carlo simulation to solve this equation, and the sample size can be as large as hundreds of micrometers. So that's in a microscale. So you can see our method is a multi-scale simulation with high predictive power. So we provide our data to our collaborators at UT Austin, where they carried out a transient thermal reflectance measurement to detect the second sound signal. So for calculations, we first solve the wave equations to theoretically calculate the speed of second sound as a function of temperature. Then we perform the Monte Carlo simulation, and we find that at 80 Kelvin, there is a strong signal with one peak, as suggested by the red line here, and it is clearly different from the ballistic response with 3 peaks. If we calculate the speed of this peak at 80 and also 100 Kelvin, we find they agree pretty well with the theoretical calculations, and they are far away from the ballistic speed. That indicates that we have successfully observed the second sound in our simulation. But if we increase the temperature to 150 Kelvin, we find that the signals we observed is basically a diffusive response, not second sound. Our data at this temperature agrees well with the experimental measurements. And the experimental work is still ongoing for lower temperatures, trying to detect second sound. That's all I have today. So we use a Monte Carlo simulation, and we can successfully observe the second sound and can provide important guidance on experimental measurements. So yeah, that's all. Thank you. And any questions?
All right, thank you. Let's open up the floor to judges or anyone else that wants to ask a question.
I was wondering why the ballistic has those 3 peaks. Is there some significance to that?
I'm sorry, why the ballistic peaks?
Why are there those 3 peaks? Is there some significance to having those 3 peaks?
Oh yeah. That's good. Very good question. So ballistic means the phonons just propagate directly without any interaction with each other. So for the phonons, there are different phonon branches. So for each phonon branches has different velocity. So these 3 peaks corresponds to different branches of the acoustic phonons.
Oh, okay, cool. Thanks.
Yeah.
I have a question if no one else does. What is it? Is there something special about graphite that's making this this prediction possible? Like, would you expect this in other of these like layered materials, MOS2, something like that?
Right, that's a very good question. So the second one only exists in what we call like hydrodynamic phonon transport, and so this transport only exists in very high thermal conductivity materials. And graphite is one of them because they have very high thermal conductivity. And for the other materials with high thermal conductivity, you can also expect this phenomenon. And especially for graphene or graphite or layered structures, like low dimensional structures, this phenomenon is significant.
All right, thank you. I'm going to go ahead and trigger the last judges score countdown, and then we'll have closing comments.
All right, thank you.
All right, thank you so much.
And thanks, Zhang, for using the template we provided and also using the tutorial for using the Zoom function.
Right, thanks. They're very helpful. Yeah.
Okay, we did it. You guys are all great. Jeremy, do you have any closing comments as well?
Sure. Well, you can see that this poster session is still going strong, but I think all of us are probably, a little tired. But I really enjoyed this this event. It was really wonderful to see, this group of distinguished presenters, and I can see that there was also a chat on the live. The YouTube live thing, which was going on in parallel. I didn't notice it until the end. And
yeah,
so,
it was mostly me.
well, that's okay, but I see there's some other people. But I really want to thank everybody, the participants, the judges, PQI staff again, for making this a really great event. And I hope we don't have any more of these. You know what I mean by that. I mean, I hope that we're not under lockdown soon, and we can start to act more normally. But in the meantime, we're going to have more events, and they're not going to be virtual events. There will be things that you'll be able to watch and participate. Speakers, distinguished invited public lectures, and other events, and we'll be announcing the winners sometime next week.
Mm-hmm.
So stay tuned to that. It'll be certainly announced in the newsletter, if not elsewhere. And everybody, thanks again. Stay safe and all of that. And I know everybody is, but yeah. So we will see you soon at some future PQI event.
Hopefully.
Yeah.
All right. Thanks, everyone.
Thank you.
Thank you.
Bye.
Thank you.
Bye.
I just want to say thanks again and well done to everyone, and especially to all the PQI staff for setting this up and putting it together. I thought that was really great. It was really neat to be a part of. And yeah.
Thanks for tuning in, from Scotland.
It was great. It was a great pleasure. It really was.
Yeah, and I really like your background. It's a great background.
What? It's an office.
Andrew. Oh, that's not a background?
No, I think that's his room.
So Jeremy and I have had a couple of Skype conversations where I've had other virtual backgrounds.
Oh, I love Star Trek.
That lead to people guessing different sort of science fiction.
That's cool.
Things.
Okay.
Just assumed that was another background. Yeah.
I thought that I'd just go with the most natural thing because otherwise it could be off-putting.
I'll have to get the Star Trek one.
Yeah. Barbara's one is really nice.
Okay, bye.
Yeah, I like that. I like them the best.
Well done, Barbara, actually.
I like them the best.
Good seeing you.
Yeah.
And
it feels so
sorry.
comfortable, like it just seeing that. I feel, feels good to see PQI space.
Yeah.
It is, and I don't get to see it this year for the meeting, and so to have it there in your background there, Barbara, is fantastic. Thank you.
Yeah, I wanna reach in and take one of the candies,
Oh.
But I know that I shouldn't.
Point.
I shouldn't. It's
all the strawberry ones, Jeremy.
I'll get cooties. Yeah.
Yeah. I'll go
I
copy.
noticed there are still 12 people watching us discuss this. As
on YouTube. Oh, I can stop streaming. I forgot.
Probably stop the YouTube feed. I don't think that there was anything particularly.
Now it's 15. Now it's 15. So
let's
people
see if
signing up.
I don't think anyone else has comments on me. No, I'll stop.
But yes, if the video is still on, congratulations to all the students. That's the number one thing. They did a great job. It's not easy.